Morning, everybody.
Hello.
Hi. Okay, let's see. Uh, let's pick up where we left off yesterday. Oop, 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 oop. I forgot to. Just a minute. Let's see here. Start recording. Oh, it says I am. All right, good. Okay. Okay. We started talking about exponentials to other bases, and there are logs to other bases too. We'll get to that today. But, okay, we're going to make the following definition. If you have a positive number A and a real number X, then we are going to define a to the X to be equal to e to the X ln of A. And we talked about why this made sense yesterday. But one of the things that I find that students get confused about is why these two functions are so different. Okay. We actually compared them on a graph yesterday. This one starts out growing, well, a little bit faster than this one, but then this one overtakes it and just really heads on off. That's why exponential growth is such a problem. Okay. Well, when it talks about things like coronavirus, it's such a problem because when it takes off, it really takes off. Okay, but why the derivatives of these functions so different? For x squared, f prime of x is 2x, and yesterday we said that g prime of x is 2 to the x times this number ln of 2, which is a constant. Okay, so the big difference is in f, the base varies. In g, the exponent is what's varying. The base is fixed. For f, the exponent is fixed. And okay, somebody needs to get it be let in. Let's see. And let me show you why this works out and that fits with this, and this works out and that fits with this. Okay, we have this definition up here. A to the x is equal to e to the x ln of A. Well, I guess I do have to assume that x is greater than 0 for this to work. But x squared then, as long as I assume that x is greater than 0, is equal to, not wearing my good glasses. I have glasses for walking around and glasses for when I had to see things up close. Okay, x squared, well, here the base is a. So here the base is x. And so it's going to be e to the 2 ln of x. Okay. This is the definition. And as long as I assume x is greater than 0, I can apply that to x squared. So the derivative of x squared is the derivative of e to the 2 ln of x. And that's equal to e to the 2 ln of x times the derivative of 2 ln of x, okay, because of the chain rule. You've got e to a function, so it's e to the function times the derivative of the function. And that's equal to e to the 2 ln of x times 2 over x. And that's equal to, okay, e to the 2 ln of x is e to the ln of x squared. Using the rule, ln of a to the r is r ln of a. Just pull that 2 up into the exponent. And then e and ln, oops, write the other part. E and ln are inverse functions, so they undo each other. And we have x squared times 2 over x, which is 2x. Okay, so that agrees with what we did before. And that's the derivative of x squared. For the other function, 2 to the x, okay, apply the same definition. And that says that 2 to the x is e to the x ln of 2. So the derivative of 2 to the x is the derivative of e to the x ln of 2 is equal to e to the x ln of 2, okay, times the derivative of x ln of 2 by the chain rule. And that's equal to e to the x ln of 2. And the derivative of x ln of 2, well, ln of 2 is a constant. X is the variable, so derivative of x is 1. Just left with ln of 2. And e to the x ln of 2, I can replace that with 2 to the x. Okay. So that's why these derivatives work this way. And in particular, somebody's going to do this. I guarantee it. They're going to say the derivative of 2 to the x is x 2 to the x minus 1. No, no, no. Okay. That's not what you do when the exponent is the variable. That's what you do when the base is the variable. The derivative of 2 to the x is 2 to the x ln of 2. And in fact, the derivative in general, the derivative of a to the x is a to the x times the constant ln of a. We also talked about that yesterday. Okay, so we have these new functions are the bases. And if we can define those, well, they're all 1-to-1. And a to the x, okay, looks like that. This would be for a greater than 1, for a less than 1, so 0 less than a less than 1. We talked a little bit about how that flips the curve around the y-axis, because, okay, this is a to the x for a greater than 1, and this is really then 1 over a to the x. If a is less than 1, 1 over a is greater than 1, is equal to a to the minus x. Okay. And there's also, well, you can think of this whole family. The bigger a is, the steeper it is over there, and the faster it goes to 0 over here. And you get this whole family of curves, and then you get your a's. What if you take them getting closer and closer and closer to 1? Well, I guess 1 to the x is actually an exponential. That's supposed to be 1. Okay. Function 2. It's not very interesting because it's constant. But the curves, once they go through that, the value of 1 and become values less than 1, then the curves look like that one. They start being this kind of thing. So yeah, so there's a whole family of functions, a to the x, as long as a is positive, a to the x, okay, and a is not equal to 1, so that's a constant function. A to the x is 1 to 1, okay. If a is greater than 1, a to the x is increasing. If a is between 0 and 1, a to the x is actually decreasing. And they're all concave up. Well, yeah, that's easy to see. Since the derivative of a to the x I'm thinking. Okay, it's easy to see if a is greater than 1. If a is greater, if 0 is less than the derivative would be, okay. That's, okay. The derivative of a to the minus x is equal to a to the minus x, times the derivative of minus x, which is minus 1 times ln of a. But what, okay. All right. It's still concave up. Something's not gelling in my brain there. Okay, so I'll come back to it later. But the important thing, as long as a is not equal to 1, a to the x is 1 to 1. It has domain, all the real numbers, and range, all the positive reals. And then that means that it's got an inverse function. Okay, so we're going to define, I don't know why I'm using red here. Let's turn it to black. Okay, let's define the log base a of x to be the inverse function of a to the x. Okay, so what does that mean? Somebody wants in? Okay, are y'all hearing me?
Yes, ma'am.
Okay, thank you, Mr. Levy. Well, okay, before I go further, any questions? Okay, I guess not. Let's go on with our definition of the log then. Let me look at my notes here and make sure I'm not forgetting to say something. No, that's about it. Okay, so if I'm defining the log base a of x to be the inverse function of a to the x, let's draw a picture. Sorry, a little bit congested this morning.
Dr. Kennedy?
Yes.
Is that log subscript A exponent x?
Yeah.
Okay.
Sorry. Yeah, that's log. Okay, I'll write it bigger. Log and then a subscript a and then x is a variable. Okay. Probably at some previous math course, you talked about this function, log base 10 of x. Do you all remember that?
Yes, ma'am.
Yes, ma'am.
Yeah.
Okay, good. Yeah, usually, but when I was, well, okay. I went to school in the dark ages. But when we started talking about logarithms, it was all log base 10. In fact, back in the dark ages, there were no calculators either. So when we started talking about logs, we got tables of logs, and they were, or we used slide rules, one or the other. But yeah, that was my introduction. And that's because our numbers are base 10, basically. But you can define logarithm for any positive number, okay? Well, except 1. 1 to the x is a constant function. It doesn't have an inverse. Well, not an inverse such function anyway. Okay, so a to the x, if a is greater than 1, looks like this. Okay, and that would be 1. So that's inverse. The way you get it is by taking all the ordered pairs of points on the curve of a to the x and switching the order. Okay, so in particular, 0, 1 is a point on the curve of a to the x. That means that 1, 0 is going to be on the curve log base a of x. And this point, you flip it over. What this does basically is reflect this top curve about the diagonal line, and that gives you your inverse function, okay? Formally, we're going to say that log base a of x is y is equivalent to saying that a to the y is x. And that's the same thing as talking about these ordered pairs. If xy is on this curve, yx is on the other curve. Okay. All right, then I have log base a of x defined. What's the derivative? The log base a of x. Well, I could differentiate implicitly the other side. Okay, can't read that. Okay. So my function is called y. It's a function of x. And then if I write a to the y is x, I've got y defined implicitly. And I can differentiate implicitly. Okay, well, the derivative of x with respect to x is 1. The derivative of a to the, okay, I'm writing what I'm doing here, differentiate. The derivative of a to the y is a to the y times ln of a, that's because of the base, and times y prime, okay, because y is a function. So y prime is 1 over a to the y ln of a. And what's a to the y? Well, a to the y is x. So the derivative of the log base a of x is 1 over x ln of a, and the derivative of a to the x is a to the x ln of a. ln of a is a constant, okay? It's not a variable. Okay, any questions now? Okay, well, let's see. Let me draw a picture. This is the picture that you get when a is greater than 1. If a is less than 1, so if you have a between 0 and 1, this is 0 less than a less than 1, then a to the x looks like that. And okay, you still, to get your inverse function, you flip it around the diagonal line. That is, you take all the pairs on this curve and you switch their order. So that's going to turn this asymptote into positive y-axis asymptote. Okay, so this would be log base a of x. But whether you have a between 0 and 1 or a greater than 1, these rules hold. Okay. And there's another useful thing. Okay. There is this rule. Log base a of x is equal to ln of x over ln of a. So you can write all these logs in terms of the natural log. Remember, a would be a constant here. And, okay, a must be greater than 0 and not equal to 1 for this to make sense. Why is this true? Okay, let's prove it. Well, we have, okay, if log base a of x is y, this is going back to the definition, that's equivalent to saying that a to the y is x. And we also had the definition that a to the, I'm going to use another letter here, a to the z is e to the z ln of a. Okay, so applying that definition to a to the y equal to x, I don't really need parentheses there. Okay, so a to the y is equal to e to the y ln of a And that means that, okay, y ln of a okay, that exponent is equal to ln of x. Yeah. And from that, it follows that y is equal to ln of x over ln of a, or that you can write log base a of x Okay, so we got some basic properties here. Let's write them down. Okay. For a to the x, a positive, a not equal to 1. The domain of a to the x is all reals. The range is the positive reals. And a to the x is a one-to-one function. It's an increasing function if a is greater than 1, and it's a decreasing function if a is between 0 and 1. And the log base a of x, it's the inverse function of the exponential function a to the x. So it has domain positive reals and its range is all the reals. Okay. The domain and the range of a function and its inverse, well, they switch places. And of course, the fact that these functions have inverses means that they're all one-to-one. And again, whether it's increasing or decreasing depends on whether a is bigger than 1 or between 0 and 1. All right, so let's do some problems. In fact, you've got a lot of homework problems on these. So how about we differentiate? Can't spell this morning. Okay. Make up some problems. How about 2 to the x times the sine of x? How about 3 to the x squared? How about a log? Oh, log base 3 of x squared. Okay. So the first one, product of two functions. So that means you have to use a product rule. And so that's the derivative of 2 to the x times the sine of x plus 2 to the x times the derivative of the sine of x. And the derivative of 2 to the x is 2 to the x ln of 2 times sine of x, and then plus 2 to the x times the cosine of x. Okay. So yeah, now that we know about these functions and their derivatives and so forth, we can do problems with them. Okay, 3 to the x squared. All right, so this is a composite function. This is of the form 3 to the g of x. And that means chain rule. Okay, so, well, the derivative of 3 to the, just plain old 3 to the x, well, let's just analyze it here. Okay, so the inside function is u equal to x squared. The outside is 3 to the u. Okay, so the derivative of the inside is 2x. And I have two variables here. Let's be careful about which one I'm talking about. So this is that u prime's not the best notation for that. How about I call it du dx? Okay. And then the derivative of 3 to the u with respect to u is 3 to the u ln of 3. So this derivative, it's the derivative of the outside function applied to the inside function, which would be 3 to the u ln of 3 times the derivative of the outside function, which is 2x. So putting back in the x's, this is going to be 3 to the x squared times ln of 3 times x squared. And I guess that would look a little nicer if we put the constant out front and maybe the x squared too, but okay. But either one. Questions? No? Are you all there?
Yes, ma'am.
Okay, you're awfully quiet. Well, let's do the third one. Log base 3 of x squared. That's another composite. Oh, and I should mention something else here too. This is, okay, different from, in fact, we'll do this one too. These two functions are different. Okay. And this one, the x squared's on the inside of the log. And here, the log is inside the squaring thing, okay? So this is a composite function. And the inside, u is log base 3 of x. Outside, u squared. So du dx, we just said that the derivative of log base 3 would be 1 over x ln of 3. And the derivative of u squared with respect to u is 2u. Okay, so chain rule says this derivative is 2u. That's the derivative of the outside function applied to the inside function. And you got to multiply it by the derivative of the inside function. Okay, so this would be 2 log base 3 of x. And then I could just write that as x over ln of 3. If I put the squaring function on the inside, okay, so now I'm looking at log base 3 of x squared. Well, one thing before I take the derivative, we had this rule, ln of a to the r is r ln of a. This rule applies to all logarithms. Okay, so base 3, base 10, whatever. In fact, that's what makes it a logarithm function. That and the ln of x times y is ln of x plus ln of y. Yeah, so this is also equal to, this 2 I can bring down, okay? So that's 2 base, so log base 3 of x. Yeah, the rule is, I guess you have to call it something different. The log base a of x to the r is r log base a of x. But if you have the raising to the r power on the outside, you can't do that. Okay, that r cannot come down. Because it's a different function. When you're raising x to a power inside the log, it can come down. Okay, so I can write this function in this way. That means I can take the derivative using either this or this. The derivative of the log base 3 of x squared. Okay, just thinking about the chain rule here. So the inside would be x squared, outside log base 3 of u, so du dx. Keep trying to write a y. Du dx would be 2x, and d log base 3 of u with respect to u would be 1 over u ln of 3. So this derivative is 1 over u ln of 3 times 2x, and u is equal to x squared. So it's 1 over x squared ln of 3 times 2x, which you could simplify. Let's see, kind of run out of room there. Can simplify to be 2 over ln of 3 times 1 over x. Okay. That's doing it without bringing the 2 down. If I use this instead, okay, so the derivative of 2 times the log base 3 of x, well, that's just a constant. So that's 2 times the derivative of the log base 3 of x, and that's equal to, okay, 2 times 1 over x ln of 3. So I get the same thing, okay, as I should. Okay, so let's see. One thing that, oh dear, okay. Didn't know I could do that. One thing I wanted to talk about today, so that you can do your homework problems. Suppose, well, we've talked about what happens when you have a constant base. Okay, and we always assume that that's not legible. Constant base, a greater than 0, and then a variable exponent. Okay, for those types of functions, the derivative a to the x ln of a. And if you switch it up and talk about x to the a, where you got a variable base and a constant exponent, then we know the derivative of those functions is a x to the a minus 1. Okay, so we can handle functions that have either a variable exponent and a constant base, or a variable base and a constant exponent. But either the base or the exponent needed to be a constant, one of them. But you can make sense of, well, this function, x to the x, as long as you require that x be greater than 0. And okay, so now I have a variable base. X and a variable exponent. Okay. So what can I do? Well, there you have two options. For one, okay, we made this definition. A to the x is e to the x ln of a. And as far as the definition goes, well, we require that a had to be positive. So that's why we require that x is positive too. But this definition works on x to the x, okay? Taking the derivative so far, we're going to take the derivative of this in a minute here, but okay, we have learned how to handle these functions as far as differentiation goes, and we learned a long time ago how to handle those as far as differentiation goes. If you have both a variable base and a variable exponent, well, I can use this definition to write x to the x as e to the x ln of x. And then I can take the derivative. Okay, so this is option 1. Well, the other option is to take the log. But that's really doing the same thing, okay? Because logs and exponentials are inverses of each other. They're so intimately related. But okay, let's see, getting ahead of myself. The derivative of e to the x then is the derivative of e to the x ln of x. This is a composite function. And in general, if you have e to the g of x, okay, we could do the inside and outside stuff if we want, but it's that, okay? So this derivative is e to the x ln of x times the derivative of x ln of x. And x ln of x is just a product of two functions. So that's 1 times ln of x plus x times 1 over x. So that's e to the x ln of x times ln of x plus 1, which is the same thing as x to the x times ln of x plus 1. Okay, and yeah, that's one way to do it. The other way, so I'm going to name this function y, and I'm going to take the log, the natural log of both sides. Okay, and I haven't differentiated, yeah. Why am I doing that? Okay, because I want to take the derivative. If I take the log, it's going to help me simplify things, and then I can take the derivative of that function. Okay, let me just do it. How it helps me simplify things is if I write ln of x to the x, well, the rules of log say that that's x ln of x, okay? Notice that that's what we got up there. That makes sense when you think about it. Okay, so I've got ln of y equal to x ln of x. I want the derivative of y, but I'm going to differentiate implicitly this, okay? Y is my function. So this derivative would be 1 over y prime, because y is a function of x. This derivative, product rule, 1 times ln of x plus x times 1 over x, same thing as you saw above, ln of x plus 1. And that means then that if I multiply both sides by y prime is y times ln of x plus 1, but y was equal to x to the x. Okay, so that's the way you handle variable function, variable exponent. One of those two ways. Any question about that problem?
Could you go back down to number 2, option 2?
Sure. Oh, didn't cross my T. Okay, got a question, Daniel?
No, just taking notes.
Okay. Y'all know, well, you know that I post the notes every day, right? Well, it's not, taking notes is good for yourself. I find that when I'm listening to a talk, if I write a few things down, it helps me pay attention. So, but yeah, I do post them every day. Let's do another.
It helps me. I feel like it helps my subconscious.
Right. For some reason, just writing things down helps me think and helps me remember things too. Okay, so yeah, you get all kinds of tricks. Sometimes talking to myself also helps. Oh, a little weird. Okay, let's see. How about this problem? Let's find the derivative. So let's do another one of these. Let me make up. Oh, how about this one? This is an interesting function. 1 plus x to the 1 over x. And again, we need, okay, we have a variable base and a variable exponent. Yeah, you're going to assume x is greater than 0. Well, the base has to be greater than 0, that's for sure. Okay, for the function to make any sense. Okay. So here's our function. Would you like to do it by writing it in terms of e first or by doing this log thing? This has got a name, actually. This is called logarithmic differentiation. So which one would you like to do it with?
Can you do it like the option 2? Like,
yes.
I understood it a little bit.
Okay, let's do option 2. So we're going to use the logarithmic differentiation. Okay, so the first thing you do is before you start differentiating at all, you take the log of both sides. And the reason for doing that is that then you can bring the exponent down. And instead of having base variable exponent, you have a product of two things involving logs. Okay, so it's somewhat simpler. So now I've got this. Okay, and now I differentiate implicitly. So the derivative of ln of y is a function, remember. So it's not just 1 over y, it's 1 over y times y prime. And then the other side, well, why don't I write that as x to the minus 1 times ln of 1 plus x. Oh, my stupid phone is ringing. From nobody. It never is. Okay. Minus minus x to the minus 2 is the derivative of x to the minus 1. And so we're using the product rule. And then plus x to the minus 1 times the derivative of ln of 1 plus x, which would be 1 over 1 plus x times the derivative of 1 plus x. But you have to use the chain rule. But the derivative of 1 plus x is just 1. Plus, okay, so I may as well write that x in the denominator. And yeah, and that's just 1. And if I wrote that x in the denominator, I guess I should write the other one. You know, you don't have to do either one. Okay, so that's minus ln of 1 plus x over x squared plus 1 over x times 1 plus x. And that's equal to, not y prime, but 1 over y times y prime. So y prime is y times all of this. And that's equal to, okay, what was the, y was 1 plus x all raised to the 1 over x. And then which is a pretty messy derivative, but that does it. What time is it? Time to go, pretty much. Okay, it's like I got 8:53 according to my clock. So I guess I should end class. Stick around if you have a question. Let's see. And we'll finish talking about, I need to look at your homework assignment and make sure I've covered everything that you have problems on. Okay, so we will wrap up anything on that assignment that I haven't covered yet. But and yeah, and then we're going to do some area stuff, and then we're pretty much done. A little bit of volumes. Okay, so class is over. If you want to ask some questions, stick around.
Have a good day.
You too.
Bye.
Bye-bye.
Have a nice one.
You too. Mr. Flores or Mr. Barton, you have questions? Well, I guess I'll end.